All right, cool. Let's start with the mahia because that's a good way to revise what we talked about in our last lesson, which was all about thinking about different techniques that we could use in organic chemistry. So we're thinking about filtering over a separating funnel. When would I want to use filtering over a separating funnel? Anybody want to take a stab at that? When I want to separate things. So in both cases, we are separating substances, and we're separating substances that are immiscible. So immiscible means they don't mix together and they don't make a solution. In the case of filtering, what we have that's immiscible would be a solid and a liquid, whereas with the separating funnel, you have the two liquids and one's polar and non-polar. So keep in mind, we want to use that filtering to catch any solids. If I was using a separating funnel for a solid, it wouldn't be ideal because I'm basically just going to clog my separating funnel. And with a polar, non-polar mixture, I wouldn't want to use filter paper because it's just going to all go through the filter paper anyway. So do kind of think about it logically when you're thinking about techniques and what you're going to use. All right. For today's lesson, we are going to be covering most of the remaining functional groups that we haven't talked about yet. The only one left over after today will be esters. So we're doing the amines, which you guys have talked about last year. Amides and acid chlorides are going to be new for this year. We'll talk about how to name and draw them, so the basic skills, but we're also going to look at their properties and their reactions because that's really important when we're thinking about flowcharts and how we would identify them. Cool. All right, so lesson plan for today, we'll start with some notes on amines. I'm going to get my little clicker because I don't think I have any board notes to write today. And we do have quite a few slides to go through. I might have some board notes, so I'll do some writing potentially. Then what else? We'll take a little break and play a game called Guess Who. I thought that'd be a fun little way to kind of recap everything that we've done so far. And then we'll talk about acid chlorides and amides, which are our new functional groups. For your final task, then you have a mahi choice, so that way you guys have a chance to have a little bit of a break. Not break, time to process, I should say. Cool. All right. So lesson plan for today, we're going to be basically looking at number 1 again, looking at those functional groups, the naming, the drawing, and like I said, we are doing acid chlorides, amides, and amines. Acid chlorides, you can sometimes be referred to as chloride, so don't be thrown off if you see that word in reference point. I don't know why, we just have multiple terminologies sometimes. All right. So first thing I want to do is just a little bit of refresher from level 2 chemistry and what amines are. So the first thing to remember is that when we are talking about our amines, sorry, I'm trying to clean up as I talk. Amines are the one with the functional group that have the NH2. So the nitrogen is what we're looking for our amines. The way we create the amines is through a substitution reaction. So we substitute out the halogen to get the amine component there. In order for me to do this, I need concentrated ammonia. So I need it to be quite high. I need a lot of ammonia. The other thing that I need is I would need it to be under high pressure. And I need to dissolve it into ethanol. Any ideas to why I need to dissolve it into ethanol instead of water? A little bit of a maybe challenging question. All right. The reason has to do with the fact that ammonia is a weak base. So when you add ammonia to water, what's going to happen? And I'll switch to the document camera so you guys can see it. I don't want this marker though. I want these markers. All right. Just as an FYI, I find it's helpful to know this extra information because it helps you retain why something is important. So when I add ammonia, which is NH3, to water, what happens, have you guys seen these arrows before? The two-sided ones? The other way you could see it is like, you draw it like that. The two-sided arrow just means it's reversible. And it also doesn't go to completion. It means, so it can go backwards and forwards. Reversible reaction doesn't go to completion. I'm just making a note of that to try to teach you that chemistry language. Most of the reactions we've talked about is just a forward arrow because the reaction will go to completion. Some of these reactions are reversible and they can go backwards. And this is an example of one that is reversible. We'll talk about this more when you guys do ocean acidification. So that's the reason why I just want to point it out. Anyway, what happens with ammonia is that it reacts with water and it will form the ammonium ion, which is NH4 plus, and then you have OH minus. So that's why we say ammonia is a weak base. You might have talked about this in ion identification because you would have added ammonia to identify the ions. And when you add ammonia, you just add a little bit of it. It's the hydroxide bit that was reacting. And so that's your base component. Now it's a weak base. So it's a weak base because it can be reversed. Are we okay with that so far? I just want to kind of refresh you on what that is. The reason why I want to refresh that idea is to kind of explain why the ammonia needs to be dissolved in alcohol instead of in water. So if I dissolve it in water, I'm going to get the ammonium ion, and that's not what I want, and it's going to be not as concentrated. If I dissolve it into alcohol, it doesn't do this reaction, so I definitely have ammonia. So it's extra information, but it helps explain the why and hopefully makes it easier to remember what's going on. So just trying to look at my little flow chart here. Here we go. We saw it a little bit before. We're thinking about those haloalkanes going into those amines. It's a substitution reaction, and you're going to need ammonia, you're going to need it in alcohol, and you're going to need quite a bit of pressure to do that. Cool? I find it's useful to see the flow charts. That's a good little reminder. All right. So what else did I want to add about that? I think we're okay for now. I also mentioned I have put these notes online, Charlie. So if you want, go to the key resources and go to my Google site, and booklet number 2 is the one you're looking for. So there is a PDF of the booklet if you guys need it, because I know you were asking for it. Cool. And you guys can like obviously open it up, make your own copy, and edit through Cami if you want to have your online notes. All right, little sidetrack. Anyway, so first off, you don't need to explain the why for any of the justifications for organic chemistry. The reason why I add this level of detail so you can kind of understand what's going on. What happens with this substitution, and with a lot of these substitution reactions, is we're looking for a nucleophilic attack. So nucleophilic attack sounds exactly what it would be. The nucleus is being attacked. You have to remember that the nucleus is positively charged, and that negative charge will be attracted to that positive charge. It will be attracted to carbon atoms that are attached to things that are very electron negative, such as bromine. So bromine is pulling those electrons closer to it, making my carbon slightly positive. So since that's slightly positive, I have the nitrogen, and nitrogen, again, is electron negative, more electron negative. It also has the lone pair of electrons, and that's going to be attracted to that nucleus. So what happens with the substitution reactions is that this ammonia is going to attack the carbon, and then there's going to be a transition state, and it's going to swap it out, and thus the halogen and the the halogen gets swapped out for the ammonia. Are we good so far with that? Now, if you don't understand that, don't worry. You are never going to need to explain that. I'm just giving you background context because I think it's good to know. Keep going. Yeah? All right. So some other refreshers about amines. You might also hear these referred to as aminoalkanes. In this case, the key thing that you're looking for is a nitrogen atom, and that nitrogen atom needs to be bonded to at least one carbon, which it should be in most cases because carbon is the main skeleton of what we're dealing with. The thing with the amines that you have to remember is slightly different is that when we talk about primary, tertiary, and secondary structures for amines, it is slightly different than when we were talking about the haloalkanes and the alcohols. So if you remember with the haloalkanes and the alcohols, we looked at where the functional group was, and then we looked at the carbon it was attached to, and we counted how many carbons that carbon was attached to. For the amines, it is slightly different. In this case, it's actually a lot easier. All you need to do is look for the nitrogen and count the number of carbons attached to that nitrogen. And that's how we classify them as primary, secondary, and tertiary. So this is an example of a primary one because this nitrogen is only connected to one hydrogen. This nitrogen is connected to 2, and this nitrogen is connected to 3. So that's how we classify as primary, secondary, and tertiary. What that means, and I'll just show you, is that if I have, for example, CH3, CH3, and I have my ammonia attached to it, this ammonia, or sorry, I should say this amine is a primary amine. Because when I look at that nitrogen, it's attached to 2 hydrogens and only 1 carbon. So slightly different rule, okay? Really important to keep that in mind because we do refer to them primary, secondary, and tertiary. Just be mindful that the term, like, it's just slightly different. Good? Okay. So if you guys remember, know the primary amines when it comes to naming and drawing them. Everything that you were given was really straightforward. You didn't have any of these complicated structures that had the nitrogen attached to 2 carbons. So the secondary and the tertiary. Now you guys can be asked questions on the secondary and tertiary because you are level 3. So I'll teach you how to name those as well. Cool. These are considered a derivative of ammonia. Most of them will be nitrogen with 2 hydrogens. Most cases they give you primary. But just be mindful that in some of these other examples, you would have maybe 1 hydrogen or no hydrogens. But the main thing you're looking for is that nitrogen. Cool. All right, and that's the general formula. What else do I have to refresh you on? Amines tend to be soluble in water because of that NH2 group, and we know that nitrogen is very electron negative, and so that provides some polarity. It's similar to the alcohols, is how I would describe it. And same pattern that you guys are used to seeing. If I increase my molecular weight, I decrease my solubility because now my carbon chain is longer. And that's the nonpolar section. The other thing to keep in mind is what they are with the different states. 1 and 2 are gases. 3 and 4 tend to be liquids, but those liquids are very volatile, so they are very easy to evaporate, and you can smell it. And amines smell horrible. They smell like rotten fish. So whenever we work with amines, we try to use the hood for it, so that way the smell doesn't get into the classroom. And then anything with 5 carbons tends to be solid, and these guys will have higher melting and boiling points compared to the alkanes because we have the hydrogen bonding that's possible with the nitrogen. Are we good so far? I know I'm going through this rather quickly, but it's just like kind of background stuff to know. Cool. Other things to kind of keep in mind is that they are a weak base, just like ammonia is. So when I put an amine into water, it will react with it, and it will take on that extra hydrogen and become a positive ion, and thus allowing the remainder of the water, the OH, to act as the base. So this is a weak base. That's useful for me to know because if I was trying to identify it, I could test it with litmus paper. Cool. Okay? So amines we can test with litmus paper. That's how you're going to find them. Cool. Here's some more different types of amines. So we have, this is just the ammonia, your primary, your secondary, your tertiary, and you can have the quaternary structure, but that's with the ammonium when it has that extra component attached to it. I'm trying to think where in my notes if we have the name. Sure that I had. We've talked about how we would make the primary amine, and that's just taking the haloalkane and reacting it with the ammonia. If I wanted to get to a secondary structure or a tertiary structure, I basically take the primary amine and I react it with another haloalkane. That then produces my secondary. And then what I could do is take the secondary, react it with another haloalkane, and that's how I produce my tertiary. I doubt they would ever ask you a question where they're wanting you to convert a primary amine to a tertiary or to a secondary or tertiary, but just so you know, that's what it would look like. I have seen examples where they have asked you to take an amine and react it with something else to make an amide. So it is important to kind of know the gist of how to put these carbon molecules together. But we'll see those examples when we're doing the amides. All right, cool. So naming the amines is pretty straightforward. The main thing is you look for where that functional group is and you're assigning the number as is. You have two choices with how you name it. You can either name it as the prefix with amino and include the carbon number, or you can name it as the suffix and use the amine suffix and again use the number. This one's really useful so that way if you have two functional groups and the other functional group is a ketone and that ketone needs to be the suffix, you have the option then of naming this as a prefix. So whatever they give you guys on the assessment, they will always give you something like an amine or an alcohol, so that way you have a prefix option. Are we good so far? All right. The new stuff then is those tertiary amines and the secondary amines and how we name them. So let's look at that. You are still following similar rules with trying to find the longest chain possible. With the longest chain possible, it needs to have the nitrogen attached to it. Anything else coming off the side chains, you treat them like branches, and instead of assigning them a number, you assign them to N, which is the nitrogen. So for example, with this one here, my longest chain is 2 carbons long. So that's where I'm getting the FN amine. Now I see that there's 2 methyls attached. Both of those methyls are attached to nitrogen. So I would call it NN dimethyl. So the 2 N's represent that these methyls are attached to carbon, or not the carbon, attached to the nitrogen, and they are single carbon length, and I have 2 of them. Does that make sense? It's basically similar to the rules you guys were using before. The only thing that changes is that instead of using a number, you're using the letter N. Do you guys need more examples of that? Or
so that's a tertiary?
That one would be a tertiary amine, yeah, because it has 1, 2, 3 carbons attached to it. Cool. All right, questions, concerns, comments? All right, shall we take a break and play a game? Yeah. All right. So we are playing a game that I like to call Guess Who. So I have written on these colored colored cards an organic molecule. And you obviously can't see your organic molecule. So the way you're going to hide your organic molecule is you're going to take a notebook. I'm going to give you some blue tack, and you're going to stick it to the back of your notebook or binder, and then you can have your piece of paper to jot down your ideas. Are we good so far with that instruction? Yeah. So you are trying to basically play Guess Who and figure out what you are. I used to stick these onto people's heads, but then that was a pain in the butt because of the blue tack leaving a little bit of a stain. So, with this organic molecule, you are trying to figure out what you have, but you can only ask yes or no questions, just like a normal Guess Who game with all the little people's faces, and you ask them, like, does the person have red hair? And then you can knock down everyone's red hair. So you're kind of doing the same thing, and you're using that to try to figure out your organic molecule. So I've given a big variety of different length carbons, carbons with branches, carbons with different functional groups, and you're trying to figure out what you have. The aim of the game is to try to figure out your molecule in as few questions as possible. So try to be efficient with the questions you are asking. So for example, instead of saying, do I have 5 carbons, you should maybe ask, do I have an odd number? So you can knock off half of the carbon chains. Does that make sense? All right. Once you think you've figured out the name of the molecule, you come up to me, you get yourself checked off, and I'm the final kind of judge, and I say yes or no, and you get yourself a lolly for getting it done because it's kind of hard to do it. So you guys will need something hard to write on. Notebook, binder, I guess SciPad would work. It's kind of squishy though. You need a piece of scrap paper to write down your kind of notes as you're trying to figure out what you are. Keep a tally of how many questions you are asking, because I want to see how many questions it takes you. And that's basically it. I'll come around and I'll give you guys a molecule. I do have different levels of difficulty. So if you feel like you want something that's going to be easier, let me know. And if you feel like you want something that's going to be harder, let me know. Because I can do that. Cool. All right. If you want scrap paper, don't forget there is that drawer. All right. So let's move on now to our final section of notes, and that's the 2 new function groups, which is our acid chlorides and our amides. As a jumping ground, the way you're going to get to the acid chlorides and the amides is going to come from the carboxylic acids. So we're using that as our pathway to get to these new functional groups. The other one that you will be using carboxylic acids for are esters, but we will do that in a later separate lesson because esters are, I would say, their own fun category on their own. All right, let me show you on the document camera what I mean by, look at our little flow chart here. We can see that we have our carboxylic acids, and our carboxylic acids are going to lead into our acid chlorides. It can also lead directly to an amide, or you can use the acid chloride to get to the amide. There's multiple ways to get to that, but that's going to be kind of our dead end point. The other one that the carboxylic acids can go to is the esters, but we'll do esters in their own separate section because they're a big kind of chunk. Cool. So let's first talk about the acid chloride. Replace the OH group with a chlorine atom, so it's an unofficial, I would say, substitution reaction. That is the general formula for it. What else did I have to say about it? When it comes to naming, it's fairly straightforward. The suffix just changes to oil chloride. So you remove the oic acid and replace it with the oil chloride. Are we good with that so far? All right. Cool. Some things to keep in mind with these acid chlorides and their properties. These guys have low melting and boiling points. If I was to compare it against a carboxylic acid, its melting and boiling point would be lower than the carboxylic acids. And the reason why is because by removing that OH, I have now lost the hydrogen bonding option. So that's why it is lower. These guys are very pungent and they are fuming kind of liquids. The other thing that's really important to note is that acid chlorides are not classified as acidic. So you will not be using pH paper to test for it directly, but there are ways that you could use pH paper to confirm it in a different way. And I'll show you what I mean in a moment. But don't be mistaken by that name for that acid chloride component. Cool. Other things, in order for me to make my acid chloride, we're going to need thionyl chloride, the SOCl2. And I'll write that down on our little flow chart so we have that as well. Where is my markers are all over here. Cool. I said it was similar to a substitution, so I'll put it in a purple color as well. So you need SOCl2, and what you're going to do is swap out the OH with a chlorine. Are we good with that so far? All right. Cool. I want to hydrochloric acid. I know a lot of people think they should be using hydrochloric acid because it provides that chlorine. But the problem is you can't use that. because the byproduct of using the hydrochloric acid will be water, and water actually reacts with the acid chlorides and reverses that reaction. So I'll talk about that in the next slide. I'm just saying you can't use hydrochloric acid for it. Has to be that thionyl chloride. So the thing about these acid chlorides is that they are extremely reactive. And that's because you have two very electron negative atoms attached to that carbon atom, the oxygen and that chlorine. So that is going to make it really subjective for those reactions. Like we were saying with the nucleophilic attack, like I said, both of these are electron negative. It pulls the electrons closer to it. It's going to expose that positive nucleus for that carbon atom, and thus it's going to be really subjective to those nucleophilic attacks. And that's part of the reason why those acid chlorides are so reactive. So that then means it can be reacted with by ammonia. It can be reacted with the water or the amino alkanes as well. And again, it's going to be another substitution reaction because we're going to take off the chlorine and we're going to put something else there. So highly, highly reactive. I'll do the example with the water first because water is a good example because this is how you would test for an acid chloride. So if I wanted to test to see if an acid chloride is present, I would add it to water and it would react violently. You would see it kind of bubble and fume and things like that, and that's because it's such a fast and harsh reaction. It would release a lot of heat, and so that's how we know if the acid chloride is there. And so you have that nucleophilic attack, and then you get that substitution, and then HCl is the byproduct. We couldn't use HCl to make the acid chloride because if you did that substitution, you have to remember that would go in, the OH would be removed, and then it would combine with the hydrogen to make H2O, and then it would just self-react. So that's why you're not using this as your reagent to make your acid chloride. Hopefully that makes sense. It's just a nice little reminder so when you're thinking about what you're doing, you know why not to do something. Are you okay with that so far? All right. When I say that the acid chloride doesn't count as an acid, if I just put pure acid chloride onto a pH paper, it wouldn't test for acid. So like if I use blue litmus paper, it wouldn't turn red. But if I have damp litmus paper, and that's the key word you're looking for, damp means there's some water in there, and if there's water, we're going to first get this reaction. It'll turn into a carboxylic acid, and then that's going to cause the litmus paper to change color. So do keep in mind, you can kind of test for an acid chloride with pH paper, but you're going to need to add water first for that to work. But the thing is, once you add water, you're going to know it's an acid chloride because of the violent reaction anyway. So you wouldn't really need to do it. All right, cool. So that's our acid chlorides. The last functional group that I want to talk about today is the amides. So amides are really special. They have both a carbonyl and an amine attachment to it. So that's what makes these guys different, is that combination. We will abbreviate it like that, for example. And these guys will also fall into the same categories like the amines did of primary, secondary, and tertiary. So again, in that case, you are counting to see how many carbons are attached to that nitrogen. So in this case, the primary has only one carbon attached to that nitrogen. A secondary has 2 carbons. A tertiary would have 3. And the way you would name them would be in a similar method to your amines. You would use that N. So N-methyl, N-propyl, or whatever. The thing with naming these guys is that the parent chain has to have the carbonyl. So it's not necessarily the longest chain, it's the chain with the carbonyl and the nitrogen. And I think I have some examples later that I'll show you. Actually, I do. Yeah, next page. Cool. And these are known as a carboxylic acid derivative because we're using the carboxylic acid to make them. All right. So when it comes to naming them, the main carbon chain needs to have the amide functional group and the full amide functional group. So the nitrogen and the oxygen. So other things things to note is that the suffix changes to amide, and then anything attached to it is known as the ends. So with this one here, let me write it on the board, or not the board, on my paper, to kind of show you what I mean. Let me just quickly copy it down so I have it on my piece of paper. And I want to show you because it looks kind of different to what you would do in other namings. Cool. First off, here's my acid chloride, and you can see here I have an amine. Is this amine primary, secondary, or tertiary? It's primary because I can see there's 2 hydrogens on there. There's only 1 carbon attached to it. I then make my the amide. Here's the amide link. So we have the carbonyl, we have the nitrogen. Is this amide primary, secondary, or tertiary? It's secondary now, because you see how that nitrogen is attached to 2 carbons. So that's a secondary amide. So we're going to talk about how we name those secondary amides. And then, what is that? I think that's just the byproduct. It must be reacting with remainder amines, yeah. All right, cool. So with the amines, you're looking for the longest chain coming off the nitrogen. In this case, you're not looking for that because you need the full function group. So this has, actually, let me add an extra carbon to prove my point. So this is technically the longest chain for that carbon, right? But we aren't going to name it based off that chain because it only has the nitrogen functional group, or nitrogen section. I need both the nitrogen and the carbonyl because that there, that's the amide. So it's going to look a little bit counterintuitive when you go to name it, that you're going to name it with the shorter chain because that's the one with the amide attached to it. So this would be N-propyl, because that is a 3-chain branch. It's attached to the nitrogen. And then since that's 2 carbons there, that'll be eth-N-amide. I don't need to specify what number it is on because it's going to be at the end. All right? Well, not the end, but like this is the end considering this is a branch. Okay? Are we good so far? Do you want another example? Yeah. Another example? Okay. I'm just going to make up a random carbon chain. Do you want me to give you one with a tertiary structure? Or primary or secondary? Again.
Maybe all 3.
All right, I'll give you a couple of versions. What is that? CH2. And I'll do this one here. Cool. So that one is your primary, and that one is a secondary, or sorry, a tertiary example. And then this one was a secondary example. Cool. And this one here, I don't have any carbons coming off of the nitrogen, so that's a primary structure. Count the number of carbons. In this case, it's only 1, so that would be methanamide. And I'm done. Okay. This one here, I have 2 branches coming off the nitrogen. Now, again, this might be the longer chain, but that chain does not have the carbonyl. This carbon has the carbonyl. So we're looking for the one with the carbonyl because that's going to be our parent. So, again, we're going to have the methanamide as our parent because that one has the carbonyl attached to it, and then these 2 are the branches. So I have methyl and I have ethyl. We put it in alphabetical order, and ethyl and methyl. I'm running out of space. Let's move that up for you guys so you can see it.
Is it methanamide or is it just methanamide?
Oh, it should be methanamide.
Yeah.
Yeah, don't make that mistake because they'll mark you down for that. Methanamide. Did you do it for the FN? I did it the whole time. Cool. All right, can I move on?
Yeah.
All right. Cool. So with these amides, I have lots of different options of how I make and add ammonia to it and heat it up. However, the easier way of doing this is to use an acid chloride and use ammonia. The reason why is those acid chlorides are extremely reactive. I won't need to add any extra reagents or heat for it. Whereas with the carboxylic acid, I would probably need to add some sort of catalyst like heat. Cool. And then the other way I can make these amides is through an ester, but you're unlikely to do that because it's not a terribly easy way to go about it. Are we good so far? All right. So here is an example of the nucleophilic attack. In this case, you are going from the acid chloride to our amides. Same sort of property of you are attacking that positive carbon. So this one here would produce a primary if I'm using ammonia. If I was using a carbon chain, so this one here is a primary amine, the acid chloride, I would produce a secondary amide. Yep. All right. Some properties with the amides. These guys have a higher melting and boiling point because we have, again, that carbonyl, and now we've returned the hydrogen, we've returned the nitrogen and hydrogen, thus allowing for those hydrogen bonds. These tend to be quite soluble then because they have that polarity. They have a lower molar mass than the amides, so they are soluble. The lower the molar mass, the more soluble it will be, which tends to be the case. And these guys are pretty odorless unless it isn't pure and you have something else cut into it. So since we use amines to make amides, if you have leftover amides, it's going to smell. If you have a pure substance, it won't smell. So again, that's a distinguishing test. The amides we will distinguish with smell and the amines we will distinguish with smell and pH vapor. Cool. The other important thing to remember about the amides is that they are neutral. So the amines will change red litmus blue. The amides will not. So be careful. They love to compare and contrast the amines and the amides because they're so similar. And you have to remember those amides, even though they have the nitrogen there, there's that carbonyl, and that's going to prevent it from being a proton acceptor. So it's not going to be basic. These guys also won't react with the hydrochloric acid. And these guys, like I said, are not basic. So make sure you are very clear on that.
Is the amine basic?
The amines are basic. The amides are not.
Yeah.
And I think in your booklets, I should have a summary chart of the identification. I don't know if it's on this lesson or a later lesson. Is it on this lesson?
No, it's on the other page.
Let me find it. Oh no, it is on here. Cool. There's really good charts because right now you guys will be able to haven't talked about yet is the esters. And esters don't really have an identification test. It's just process of elimination because they're very unreactive. So you guys can now, on the No Brain Too Small, do collated questions on identification tests. I've printed this in color because I think it's useful to see the dichromate, permanganate, and the chromium, just to help give you a guideline. But basically, this summarizes how would you test for the different functional groups. Are we good so far? All right. The other thing that I've included is this page here that I thought was useful. Because if you're mindful, a lot of what you look at when you do your identification test is you want to think sequentially what's the most efficient way to test something, and also do that compare and contrast component as well. So this is a nice setup because it kind of shows you, which molecules would be insoluble. So when you mix them together, you can say this one, and this one won't mix together. I then do this next test to then confirm which of those three it is. So this is a nice way to kind of get you to see which ones will and won't react and kind of plan your attack for your testing. Does that make sense? All right, I'm mindful that we're running out of time, so we won't have time for the Mahi choice, but that's okay. iPad pages on here. Now there's a lot listed. I don't obviously expect you to do all of them. I would say tackle it based off of the functional groups you're struggling with. 181 and 187 is much more scaffolded and more basic material. 188 to 192, that one's a little bit more complicated application of content. There's also ESA stuff, but if you are trying to kind of show me evidence for excellence, move on to the NCA questions. And in fact, now at this point, you can do a lot more of the organic chemistry questions because we've covered all but one functional group. So you can do basically all of the flow charts. You can do any of the technique questions. You can actually do identification questions now as well. So feel free to do anything that you feel would be helpful. Please provide me evidence. You can either put it online or drop it in my box. But to summarize today, we have 3 more functional groups you should add to your repertoire. You should name them, be able to draw them, tell me their properties, tell me their reactions, how would you identify them, that sort of thing. All right, cool. Go ahead and pack up. Make sure you wipe down my tables so the spray bottle's on the side.